Hey everybody, we're going to be talking about in this video why the atomic mass for elements has a decimal. When you look up at the periodic table, you'll see a decimal for atomic mass. Why is that? We're also going to be talking about something called isotope abundance. So let's get to it. So when you look up at the periodic table, you'll see each of the little boxes that an element lives in. There are three things always. Often there's other information, but there's always three things. One of those is the symbol for the element, and that'll either be a capital letter or a capital letter and a lowercase letter, depending on the syllable, depending on the element. There's going to be a whole number. That whole number is the atomic number. And then there will also be a number that is a decimal, and that is the atomic mass. So one of the things we're going to try to answer today is why? Why is there a decimal right there for atomic mass? And what are the units for atomic mass anyway? So if the atomic mass of carbon is 12.01, like we were just saying, what will the units be? So as you can imagine, atoms are really, really, really small. And if we express them in conventional mass units like grams, we'd have some really small numbers. And so something was created expressly for the purpose of expressing these masses that are so very small. And they are called an atomic mass unit, or AMU, or these days, just U, as it says down here. So what is an atomic mass unit? Here's the definition. The definition is that it's 1/12 the mass of the isotope carbon-12. And what that means is carbon-12 is defined as exactly 12 AMUs. So that isotope is 12.00000 forever AMUs, and all other atomic masses are relative to that. Why carbon-12? Actually, it hadn't always been carbon-12 as the standard. It was oxygen-16 for years, and it was hydrogen-1, but it's been carbon-12 since the early 60s. To help us understand a little bit more about what an AMU is, here's another way to think about it. So carbon-12, because of the mass number there, that means it has 6 protons and it has 6 neutrons. Remember, a neutron's and a proton mass are about the same. So there are 6 plus 6, there are 12 nucleons in the nucleus. And since carbon-12's mass is 12U, we can say that one AMU, or U, is about the mass of one proton or one neutron. So that's another way you can think about what an AMU is. It's about the same mass as one of those subatomic particles, a proton or a neutron. So there are actually 2 common isotopes of carbon. One of those is carbon-12. Here's its nuclear symbol right here. And notice that its relative atomic mass is 12U. Remember, that's our standard. We talk about these as relative atomic masses because it's relative to carbon-12. And so the relative atomic mass of carbon-13 is 13U's. Actually, way back here there's a 1, but that's so far back that we're just going to go with, this is plenty of precision for us. So here's the deal. If we have a sample of carbon and it's analyzed using something called a mass spectrometer, we can figure out in that sample of carbon what percent is carbon-12 and what percent is carbon-13. So using this instrument called a mass spectrometer, it was discovered that in the sample of carbon that we were analyzing, 98.9% of it is carbon-12. The other 1.1% is the isotope carbon-13. So the next slide, we're going to talk about how we're going to use these 2 pieces of information to find the atomic mass of carbon that we're used to seeing on the periodic table. So here's how we would set it up. So here's the same information we had on the slide before, and I want you to pay special attention to how we set this up because the setup's the same for all problems of this type. So right here we can see that 98.9% of the carbon in our sample was carbon-12. And you remember from the previous slide it said the relative atomic mass is 12.00. So the first thing we're going to do is to write the relative atomic mass of carbon, 12.00, and multiply it times our percentage. But we want to express that percentage not as a percent. We want to express it as 0.989. And then we're going to close our parentheses, and then we're going to do the exact same thing with the other isotope of carbon. I don't know if you remember from the previous slide, but its relative atomic mass is 13. So I'm going to put 13 here and multiply it times its percentage. Moving the decimal back 2 places there gives us 0.011. And then when we do the math, when we multiply this and multiply that and then add them together, guess what we get? We get 12.01, which is what we see as the mass of carbon on the periodic table. So really, the atomic mass that we're used to seeing on the periodic table is kind of like an average that includes all the isotopes that are present that we're aware of. And so that's why carbon is not exactly a whole number. None of the elements are there because all of them has isotopes that make up part of their mass. They're considered as well. So here's a problem for us to work. Remember the setup we used in the last problem? We're going to do the same thing here. But this one is about bromine. And it says bromine has 2 isotopes. One of them is called bromine 79. Here's its relative mass. And the other is bromine 81. Here's its relative mass. And it tells us that bromine 79 has an abundance of 50.69. I'm going to write that down. Bromine 79 is 50.69. Hey, if there are only 2 isotopes, I guess then we know the percent abundance of the other one, even though they didn't tell us. If there are only 2 isotopes and one of them is 50.69, the other one is 100% minus that. So what would that be? 49.31%. So I just subtracted from 100 to figure that out. Now that we have all this information, let's find the average mass of bromine. In other words, the mass that we see on the periodic table. And so we're going to take bromine 79's relative mass and multiply it times its percent abundance, which is right here, 0.5069. Okay? Then we're going to do the exact same thing for bromine 81. So the relative mass that told us up here for bromine 81 is 80.9163. And then we're going to multiply times the percentage as a regular number instead of a percent. So that's 0.4931. And then close those parentheses. So let's do some math and see what we get. And we get 79.904 U, or AMU. And if you look at the periodic table, find bromine up there, that's the average atomic mass that you'll see for bromine. So now let's do one that has 3 different isotopes. So up here we got magnesium. Here's their relative atomic mass and the respective percent abundance that goes with each of those. And so when we set this up, I'll start with magnesium 24. There's its relative atomic mass. And I'm going to multiply by it 0.7870. And then I'm going to add to that and do the same thing for magnesium 26. 25.983 times 0.1117. Put that as a regular number. And then I got one more since we have 3 isotopes, and that's going to be that relative mass, 24.986, multiplied times its percent abundance, which is 0.1013. So do you see it's just the same thing we did on the previous couple of examples. We multiply the relative atomic mass by their respective percentage. Now let's do some math and see what we get for our final answer. and we get 24.31. And if you look up at the periodic table, you'll notice that's the same thing it has for the average atomic mass of magnesium. Okay, last example. This is a little bit different. We're going to be solving for something besides the average mass. So let's take a look. It says bromine has two isotopes. Here's the relative atomic mass of bromine 79, and there's its percent abundance. And it says, using the average atomic mass on the periodic table, determine the mass of bromine 81, the other isotope. Well, since there's only two isotopes and one of them is 50.69, we can figure out the other percentage by doing a little subtraction, and that turns out to be 49.31. And so bromine 81, that's the percentage, but we got to figure out what its mass is. So the setup is going to be the same. Let's use bromine 79 first. So there's its relative atomic mass, 78.918, and we know the percentage because they gave it to us. And let's put that as a regular number, take it out of a percent, 0.5069, close parentheses. Plus, now here's where things are different. We don't know the relative atomic mass of bromine 81. That's what they're actually asking for. And so we can't write anything here except a variable x, and that's what we're going to be solving for. Now we do know the percentage of bromine 81. We figured it out right here, and we subtracted from 100. So that's 0.4931. Now we can't have two unknowns in this equation, so this has to be equal to something. And what it's equal to, you can find just from looking up at the periodic table. So you look at the periodic table, you'll notice the atomic mass, the average mass of bromine is 79.90 AMUs. But now, in our equation, we have everything except this x, and so we can now solve for it. So let's get to work doing that. So when I multiplied this, I got 40.00. My calculator just died. Hold on one second. Okay, so that's the product of that, and then plus this thing right here. Now, since we don't know what x is, we're going to say 0.4931x. We're just going to multiply those together. And then we set it equal to this, the mass that we got from the periodic table. Okay, and now we want to solve for x. So first, we're going to subtract 40 from both sides. So that's going to leave 0.4931x over here, and it's going to leave 39.90 over here once we subtract 40 from both sides. And then we have to solve for x by dividing both sides by 0.4931. Let's see what we get. And what we get is 80.92 AMUs. That would be the mass of the other isotope, bromine 81. All right, everybody. Thank you for watching.